Good morning. Today let us discuss about asynchronous counters and its design. First of all, let us discuss about the classification of counters. Counters can be divided into two, asynchronous counters and synchronous counters. In asynchronous counter, only first flip-flop is clocked by an external clock. All subsequent flip-flops are clocked by the output of preceding flip-flop. Asynchronous counters are slower than synchronous counters because of the delay in the transmission of the pulse from flip-flop to flip-flop. Asynchronous counters are also called triple counters because of the way the clock pulse ripples it through the flip-flops. Now let us see what is synchronous counters. In synchronous counters, all flip-flops are clocked simultaneously by external clock. Synchronous counters are faster than asynchronous counters because of the simultaneous clocking. Now let us discuss about states, modules and the number of flip-flops used in a counter. The number of flip-flops determine the count limit or the number of states. For example, the states of a given counter is equal to 2 raised to the number of flip-flops. Of these states, we are using some states alone, that is called the modulus of the counter. For example, in a modulus 12 counter would count from 0 to 11, that is 00000 to 1011, and requires 4 flip-flops. Using 4 flip-flops, we will get 16 states, out of which 12 states alone are used. Now let us see the basic type of asynchronous counter. It's a 1-bit asynchronous counter or a mod 2 counter. This counter uses a JK flip-flop configured in toggle mode. In this, the J and K inputs are connected to high state to enable toggling. This is a negative edge triggered flip-flop, so whenever the clock input hits negative edge, the corresponding output will toggle like this. So here the first clock hits the negative edge, the output will toggle from 0 to 1. For the second pulse, clock edge will toggle from 1 to 0 like this. Next is 2-bit asynchronous counter or a mod 4 asynchronous counter. In this we are using 2 JK flip-flops which again configured in toggle mode. That is, both J and K inputs of both the flip-flops are connected to logic high state. In this, the first flip-flop alone is fed from an external clock. The clock input of the second flip-flop is connected to the Q output of the previous flip-flop. Here, whenever the clock inputs hits a negative edge, the corresponding output will toggle. For example, the Q1 will toggle when the clock input hits a negative edge. Here, the output toggles to 0 to 1. For the next negative edge, again, this will toggle from 1 to 0, then 0 to 1, likewise. And this Q1 will act as the clock input for second flip-flop. So when this Q1 hits a negative edge, Q2 will toggle from 0 to 1. For the next negative edge of Q1, it will again toggle from 1 to 0 and likewise. So this is a mod 4 counter. So it will count from 0, 0, then 0, 1, 1, 0, then 1, 1. That is, it will count from 0, 0 to 1, 1. For the next clock input, it will start over from 0, 0. Next is 3-bit asynchronous counter or a mod 8 counter. Here all the flip-flops are configured in toggle state. So for the first clock input, when first clock input hits, the output A toggles from 0 to 1. For the next clock input, it will toggle from 1 to 0, 0 to 1 likewise. This is connected as the clock input of the second flip-flop second JK flip-flop. So for the when the output A toggles from 1 to 0, B output toggles 0 to 1. Then again for the next clock pulse, it will toggle to 1 to 0. This will act as the clock input for the third flip-flop. Again, which causes the toggling of flip-flop, third flip-flop, like this. So using this 3-bit asynchronous counter, we can count up to 00 to 111. Now the main disadvantage of asynchronous counter is ripple effect. That is, in the previous cases, we have considered all the flip-flops are ideal flip-flops, but in actual practice there will be a delay for every electronic component. So it will take, for a flip-flop to respond to a clock input, it will take some time. It won't respond ideally like this. It will respond like this. That is, for a 3-bit counter, for when the first clock edge hits the negative edge, the Q0 output will take some time to respond. When this changes from positive to negative, Q1 will take some more time like this. So we can see that the delay is cumulating from Q0 to Q1. Again, when Q1 is hitting the negative edge, Q2 will take some more time to respond. So all these delays are getting cumulative. Now we will see how we can configure a D flip-flop as a counter. In D flip-flop, to configure it as a counter, again it should be in toggle state. For that, we should connect the Q bar output of D to Q bar output of D flip-flop to D input of D flip-flop, and everything else is same. So we can increase the number of we can increase the modulus by increasing the number of flip-flops. Now we will see various examples. First of all, we will see how we can configure a 4-bit up counter with negative edge triggered flip-flop. Then a 4-bit, how we can get a 4-bit down counter with negative edge triggered flip-flop. Then modulus for up counter with positive edge triggered flip-flop, and modulus for down counter with positive edge triggered flip-flop. Then how we will get a truncated counter. Then we will concentrate on counter design. This is 3-bit up counter using negative edge triggered flip-flop. Here, as we said, this basic element is JK flip-flop. JK flip-flop is configured in toggle state. Now, in order to make it an up counter, we should connect the Q output of each stage to the clock input of next stage. So this will give you an up counter which counts from 000 to 111. Now we can configure the same negative edge triggered flip-flop as a down counter by connecting the Q bar output of previous stage to the clock input of next stage, like this. All the flip-flops should be in toggle state. So this will give you a counter, a down counter, which 3-bit down counter which counts from 111 to 000. Again, if we are provided with the positive edge triggered flip-flop, we can configure it as an up counter by connecting Q bar output of previous stage to the clock input of next stage, like this. So here also the JK flip-flop should be configured in toggle state. So this will count from 000 to 111. The same positive edge triggered flip-flops can be configured as down counter by connecting Q output of previous state to the clock input of next state. So here also the JK flip-flop should be connected to logic high state to ensure toggling. This counter also count from 111 to 000. Now we will see how we can truncate the number of states. This is a 3-bit counter which will count from 00. This is actually a 3-bit counter which will count from 000 to 111. And how we can truncate this into a, this is actually mod 8 counter, how we can truncate it to a mod 6 counter is shown here. This counter, all configuration will count from 000 to 101. On reaching the count 101, it will reset all these flip-flop. That is, it will sense the count 6 here. and it will reset all the flip-flops. For that, a NAND gate is used here. When all the flip-flops of all the inputs of a NAND gate is 1, the output will be low. So which is connected to the reset input of all other JK flip-flop, that will ensure the resetting of the flip-flop. To obtain 1 1 here, the count detected is 0 1 1, and corresponding to that it will generate a reset pulse. Now let us see the design steps of asynchronous counter. First is we should select the type of the counter. It should be whether it should be an up counter or a down counter. Then we have to determine the modulus of the counter. Then we have to select the type of flip-flop. It can be JK or D or any other flip-flop. Then we have to select the type in the sense the positive edge or trigger flip-flop or negative edge trigger flip-flop. Then we have to determine the number of flip-flops. The relation to obtain the number of flip-flops is equal to 2 raised to number of flip-flops should be greater than the modulus of the counter. Now the next step is how we should connect the flip-flops. To obtain the down counter, in the case of positive edge triggered flip-flop, we should connect the Q output to the clock input of next flip-flop. In the case of negative edge triggered, we should connect Q bar output to clock input. In the case of up counter, for negative edge triggered flip-flop, we should connect Q output to clock input of next state to obtain up to configure it as an up counter. In the case of positive edge triggered, we should select Q bar output as clock input for the next state. Then design limit or the limit logic. How we should apply the limit logic. Input to the logic is the count that is 1 past the end of the sequence. That is, if we require mod 13 counter, we should detect a count on mod 14. We should detect count 14 for resetting the circuit. For example, let us design a mod 14 counter, mod 14 up counter, and let us say select JK flip-flop for the same. Then let us take a positive edge triggered flip-flop. Here we have to, here we will get the number of flip-flops as 4, because we are selecting a mod 14 counter which is less than 2 raised to 6, 2 raised to 4, that is 16. And here we are going for an up counter, so we would we will select Q output to clock input of the next, we are designing an up counter for mod 14 up counter. And the design limit logic is it should detect the count 14, that is 1110. So this is mod 14 up counter using positive edge trigger D flip-flop. Here we have detected the count 1110, and detecting the count, the NAND gate will apply reset pulse here, and all the D flip-flops are configured in toggle state. For that, Q bar output of all the flip-flop, each flip-flop is connected to the D input like this. So by this you might have a clear idea about what is an asynchronous counter, what are the design steps involved in asynchronous counter. Thank you.